So, and that means that the function has a reflection across the line y equals x. Algebraically, remember, you switch the x and the y in the equation, and then you solve for y. So algebraically, that's how you find the inverse function. So again, one notation that you talked about last year to represent inverses is that f to the negative 1 exponent of x. Remember that notation that you saw last year? Remember, this is not equivalent to 1 over f of x. This is the one time when you see a negative exponent, you do not take the reciprocal. So remember, that's just the notation you saw last year for inverse function. So for example, if you take a look at the function x to the third, you guys graphed the cubic function last year. X to the third, remember, looks something like this. So this was your graph of x to the third. So then to find the inverse function, remember, we're going to switch the x and the y. So this would be equal to x equals y to the third. So then how would I solve this for y? What would I do to both sides? I would take the what? Cube root. So then y is equal to the cube root of x. So the inverse then for x to the third is the cube root of x function. So that's what the inverse for x to the third is going to be. So if you were to sketch x to the third looks something like this. And again, there's that line of reflection, y equals x. So far, nothing new, I hope. You guys remember kind of doing this a little bit last year? Yes, hopefully?
What is y is -1? Is that f to the -1?
Remember, this is just your notation for inverse. So remember that f to the -1 says that this is the inverse for function f.
Well, I'm saying that x opposed to the -1.
That's f of, well, you always have, when you have function notation, remember, you always have the independent variable inside parentheses. And then you also learned last year a composition rule for functions and inverses. Remember, when you take a function and do a composition with its inverse, they will be equal to x. So in other words, if I take my cube root of x and I plug it into function f, so remember, by your input notation, if I take cube root of x and plug it into x to the third, that will give me that x. So remember your composition rule, when you take a function and you do a composition, it will give you x. And again, this is the one time where composition would be commutative. If you take the inverse function and you plug in f of x, it would be equal to x. So in other words, if I take my x to the third and I plug it into the inverse function, so then when I take the cube root of x to the third, that would also give me x. Hopefully cleaning out some cobwebs of stuff we talked about last year. As I mentioned a few minutes ago, because when you do inverses, you switch the x and the y. Remember, the domain in f of x becomes the range in your inverse. The range, which are your y values, and f of x become the domain of the inverse. So up till now, hopefully I haven't hit on anything that you haven't talked about from last year back in Algebra 2. Yes? This is where, depending upon your background, if you came from Algebra 2 honors versus regular Algebra 2, this may be a new piece for you if you had regular Algebra 2. Not all functions will have an inverse. So in other words, what happens, in order for an inverse to be a function, it must be a function that is one-to-one. So in regular Algebra 2, you guys did not talk about one-to-one functions very much. Remind me again, what's that vertical line test? I know everybody's heard about a vertical line test. What does that vertical line test do, Jed?
It's where the 2 points or 2x coordinates are the same coordinates.
Exactly. So remember, we can test whether or not a graph is a function if that vertical line intersects a graph at more than one point. We know it's not a function because that means you have the x values repeat. Well, in other words, for a function to be one-on-one, it not only has to pass the vertical line test, but it has to pass the horizontal line test. So in other words, for a function to be 1 to 1, what has to happen, first of all, it's got to be a function, so it's got to pass the vertical line test. So the horizontal line test is very similar to the vertical line test. That horizontal line can only intersect your graph at one point to be 1 to 1. So in other words, to be a 1 to 1 function, none of your x values can repeat, none of your y values can repeat. That's what makes a 1 to 1 function. So again, but even if a function is not 1 to 1, we can restrict the domain and force it to be 1 to 1 in order to find the inverse. Perfect example is x squared. We all know what the graph of x squared looks like. So you agree with me, it passes the vertical line test. It's a function. But now if I try and see if it passes the horizontal line test, does that horizontal line intersect the graph at more than one point? Yes. So it's still a function, it's just not 1 to 1. So it's just not a 1 to 1 function. It's still a function, it's just not a 1 to 1 function. However, what we can do is I can say, well, let me restrict the domain for x squared. So let me say, you know what? Let me just make the graph of x squared for my x values greater than or equal to 0. So I'd be looking just at the right-hand side of the parabola. Now, would you agree with me that it would pass my horizontal line test? Still the same function, it just has a restricted domain. So now this is 1 to 1. Now, the reason why we're talking about 1 to 1 functions is we've got a problem with all of our trig functions. They're all functions, but they're not 1 to 1. So when we talk about the inverse trig functions, what has to happen is we have to restrict the domain for all of our trig functions in order to talk about the inverse, to force them to be 1 to 1. So let's talk about sine first. And the way I always like to talk about sine is we spent a lot of time back in Unit 2 graphing. Remember what the graph of sine of x looks like. Remember, it started at the baseline, went to the maximum, baseline, minimum, baseline. Remember, that's what the parent function for sine of x looked like. And that goes from 0 to 2 pi. I can also graph more than one cycle going from negative 2 pi to 0. So do you agree with me that sine of x is not 1 to 1? It will not pass my horizontal line test. So in order to talk about the inverse sine function, what we're going to do is we're going to restrict the domain. So we're going to restrict the domain from negative pi over 2 to pi over 2. So again, right here is my negative pi over 2. Here's positive pi over 2. So at negative pi over 2, sine is negative 1. At 0, it's 0. At positive pi over 2, it's 1. By me restricting that domain, would you agree with me that now it is a 1 to 1 function? Yes. So now let's take a look at the graph of my inverse sine of x. I'm going to write it underneath, my staple's getting in the way. So now remember, on this graph, I've got the point negative pi over 2, negative 1. You told me a few minutes ago we find the inverse by doing what? We switch the what? X and the y. So then on the graph of the inverse function, I'm going to have the point negative 1, negative pi over 2. 0, 0 will still be 0, 0. And then I have the point pi over 2, 1, so that on the graph of the inverse, it's going to be 1 pi over 2. And the graph is going to look like this. So that's what your graph of the inverse function looks like. Okay? So that's the issue we run into with these inverses. All right? The picture, for me, helps me remember why, when I talk about the unit circle in a few minutes, I can't be looking everywhere in the unit circle. I always go back, what does it mean to have an inverse? It's got to be 1 to 1. Remember what the picture of sine of x looks like. Sine of x is not 1 to 1 without restricting that domain. So that helps me remember that, wait a minute, I can't be looking everywhere in the unit circle anymore. Remember, sine of x has a domain of all real numbers. The range goes from -1 to 1. So we talk about the parent function for sine of x. The domain was all real numbers. The range is -1 to 1. So the domain restriction, to force it to be 1 to 1, is going to go from -pi/2 to pi/2. So when we talk about the inverse function, remember the domain and range are going to switch. So the domain of your inverse sine is the same as the range for sine of x. The domain is going to be -1 to 1. The range is going to be that restricted domain of -pi/2 to pi/2. We're going to do composition later on. We'll come back and talk about the composition, but let's talk about inverse sine. Now, inverse sine has a couple different notations. Another very common way that you will see inverse notation for your trig functions is you may see this -1 exponent, or you may see this arc sine of x. Those of you that have taken the, if you ever take the SATs, that has the trig in it, they're going to use arc sine, not that sine to the negative first. So it still means different textbooks will use different notations, but this is just the inverse. So what this means is that just like you had to memorize unit circle values, you're going to have the inverse values to remember. But with the inverses, what's happening is you can only be looking from -pi/2 to +pi/2. So quadrant 2 and quadrant 3 are going to be dead to you when it comes to inverse sine. So what happens is now basically you're doing the unit circle backwards. So when you see this question, arc sine of -1, the question that's being asked is what angle has a sine value of -1. So instead of you telling me what the y coordinate is at a particular angle, I'm giving you the y coordinate. You've now got to spit the angle out to me. Your output is the angle because remember we've switched the x and the y values. But now remember your values can only go from -pi/2 to +pi/2. So the only angles that exist for inverse sine are going to be your -pi/2, -pi/3, -pi/4, -pi/6, and 0. Or in quadrant 1, you can say pi/6, pi/4, and pi/3. Those are the only angles that exist for inverse sine. So the good news is there's fewer values to memorize than you had from the original unit circle. The trick is you've got to remember from -pi/2 to pi/2. So now you tell me, what angle has that sine value of -1? -pi/, remember sine is your y coordinate, so where is your y coordinate equal to -1? It's down there at -pi/2. And remember, this is a quadrantal. So now inverse sine, again, remember, inverse sine is negative down here in quadrant 4. So when you see inverse sine of a negative, you can only be picking angles down here in quadrant 4. So in quadrant 4, what angle has that sine value of -√3/2? Is it -pi/3, -pi/4, -pi/6? -pi/, which one is it? You have three choices, negative pi over 3. And again, that's quadrant 4. It's negative, so I'm still in quadrant 4. So which angle down here has that assigned value of negative square root 2 over 2? Is it negative pi over 4 or negative pi over 6? Negative pi over 4. And that's in quadrant 4 because it's negative. Process of elimination. The inverse sign of negative 1/2 is going to be what? It's going to be what? Negative pi over 6. Again, that's in quadrant 4. So arc sine of 0 then is just going to be what? 0. And again, that's your quadrantal. That's right there on that axis. So now notice all these values are positive, so I'm moving out of quadrant 4, and now I'm picking the angles in quadrant 1. Which angle has the sine value of 1/2? Pi over 6. And again, that's in quadrant 1. Arc sine of square root 2 over 2 is going to be pi over 4. Arc sine of square root 3 over 2, that's going to be pi over 3. And then finally, arc sine of 1 is going to be pi over 2. Those are the only values that exist for arc sine. Remember, inverse sine does not exist in quadrants 2 and 3 because of the restrictions we placed on sine of x in order to make it a one-to-one function. It is not okay if I ask you for arc sine of negative 1 for you to say 3 pi over 2. It is not even it's not a discussion. Remember, at 3 pi over 2, sine is not a one-to-one function, so it can't exist. So when you're talking about inverse sine, it's got to state negative pi over 2, not 3 pi over 2. Because at 3 pi over 2, sine is not a one-to-one function. The inverse does not exist. It's got to be these angles only. Okay? So any questions on that? All right. Unfortunately, cosine does not have the same restrictions as sine. Remember, this is what the graph of cosine x looks like. If I graph it from negative 2 pi to positive 2 pi. So you agree with me, it does not pass the horizontal line test. Milo, you may want to be writing some of this down. This is not going to be something you're going to be able to remember. You agree with me, it's not a one-to-one function. So if you look at this, it would be nice if cosine and sine was one-to-one in exactly the same places. But look at this from negative pi over 2 to pi over 2. Would it be a one-to-one function if I restrict it from negative pi over 2 to pi over 2? No, unfortunately not. So the domain restriction we placed on cosine of x is going to be from 0 to pi. So if I restrict the domain from 0 to pi, do you agree with me now that this is a one-to-one function?
Yes.
Yeah. Okay? So what happens with cosine, we're restricting it just from 0 to pi. So again, when I take a look at the graph of the inverse cosine of x, remember the points that I have on cosine of x, it's 0, 1. So then on the inverse, it's going to be 1, 0. Then I've got the point pi over 2, 0. So that I'm going to have the point 0, pi over 2 on the inverse. And then I've got the point pi negative 1, so it's going to go from negative 1 to pi. So this is what your graph of the inverse cosine is going to look like. So for cosine x, remember the domain is all real numbers. The range went from negative 1 to 1. As as I showed you, the cosine of x is not a one-to-one function. So I'm going to restrict the domain to go from 0 to pi to force it to be one-to-one. So then the inverse cosine's domain will be the same as the range for cosine of x, so it goes from -1 to 1. The range is that restricted domain of 0 to pi. Again, we're going to do composition later on in the unit, so we'll talk about the composition rules later. Just like for inverse cosine, you also have to recognize that this notation, arc cosine of x, it means the same thing. And the reason where that arc comes from, just like for that arc sine, you're only looking at half the unit circle. So it looks like an arc. So that's why they call it the arc sine or the arc cosine when they're talking about the inverses. That's where that arc comes from, because you're only looking at half a circle. So unfortunately, we're in different locations than the inverse sine. Quadrants 3 and quadrant 4 are dead to you for inverse cosine. So for inverse cosine, we're only looking 0, pi over 6, pi over 4, pi over 3, pi over 2. So you're looking in quadrant 1 just like for the inverse sine. But then if you're dealing with inverse negative values, you're moving into quadrant 2, so you'd be looking at 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Those are the only angles that exist for your arc cosine or your inverse cosine. That's it. So it's different than your inverse sine. So you do have to know where you're allowed to be in which angles. So let's take a look first of all at inverse cosine of 1. Just like inverse sine, the question you're asking yourself is what angle has a cosine value of 1. And it can only be one of those choices that I've highlighted from 0 to pi. So I'm giving you the x-coordinate. So this is your x-coordinate. You've now got to tell me the angle. What angle has that x-coordinate of 1? 0. So your arc cosine of 1 then is 0. And again, that's a quadrantal. That's right on your quadrant. So arc cosine of square root 3 over 2. What angle has that x-coordinate of square root 3 over 2? Pi over 6. And again, that's in quadrant 1. What angle has the cosine value of square root 2 over 2? Got to be in quadrant 1, so which angle is it? Pi over 4. Arc cosine of a half. What angle has that cosine value of a half? Pi over 3. So that takes care of all the angles in quadrant 1. Inverse cosine is 0. So what angle has that x-coordinate of 0? That's going to be at what angle? Pi over 2. So now I'm moving into quadrant 2. So what angle in quadrant 2 has the cosine value? Because cosine's negative in quadrant 2. What angle has that cosine value of -1/2? 2 pi over 3. The x-coordinate, negative square root 2 over 2, in quadrant 2 is going to be at what angle? 3 pi over 4. And then the arc cosine of negative square root 3 over 2 is going to be 5 pi over 6. And then the inverse cosine of -1 is pi. Again, remember, inverse cosine does not exist in quadrants 3 and 4. And that's because of the restrictions we had to place on cosine of x in order to make the function a one-to-one function. Okay? So this is, like I said, just your introduction to the inverse functions. All right, we'll talk about the tangent and the cotangent when we come back from Thanksgiving break. All right, so that's where we are with those.